This flowchart outlines structural engineering's core objective, combining members to resist external loads. It branches into two disciplines. Analysis calculates internal forces like shear and bending moments. Design uses those results to fix the physical dimensions required to withstand them. Accurately analyzing a structure requires isolating the external push from the internal response. An external force applied to a surface is pressure, a scalar quantity acting in a single normal direction. This comparison table highlights the distinction. Stress defines the internal resisting force acting per unit area. Acting in both normal and tangential directions, stress is classified as a tensor, a multidimensional response developing only because the material actively resists deformation. This classification chart maps how that internal resistance manifests. It branches into direct stresses, such as the normal and shear stresses shown on these cylindrical sections, and indirect stresses, like the bending and torsional shear stresses acting on the beam. Measuring the external push on a building is insufficient to predict failure. Engineers must mathematically map the invisible, multidimensional internal resistance of the material itself. We see this internal resistance on this 3D block. Under an axial tensile load, it undergoes normal strain, elongating along the primary axis. Simultaneously, it contracts along the y and z axes. This 1D pull triggers 3D geometric distortion, governed by Poisson's ratio. This 3D cube diagram shows how these axes combine. Adding a strain in the x, y, and z directions cancels out the original dimensions. This yields the total volumetric strain formula. EV equals the sum of the strain on all three axes. This page details how mathematical logic shifts for different geometries. For a cylindrical bar, volumetric strain incorporates the change in diameter, equaling longitudinal strain plus 2 times lateral strain. For a spherical body, the volumetric strain is exactly 3 times the radial strain. Because a simple 1D pull triggers a 3D volume change, engineering failure analysis is a multidimensional problem. While normal strains change material's volume, other forces distort shape without altering the total volume at all. These sketches illustrate shear strain, which occurs when a tangential force alters the angle between mutually perpendicular planes. This angular displacement is quantified as phi. Measured in radians, it represents the sum of the angular changes shown in these complex shear diagrams. Structural materials possess independent breaking points for shape distortion versus volume compression. Isolating angular shear is necessary to identify these specific failure limits. A ductile steel rod undergoes extreme tension. The rod narrows intensely at the center, a process called necking, before snapping in a classic cup and cone fracture. We deconstruct this failure by graphing the stress-strain curve. The standard nominal curve assumes a constant area, but the true stress line diverges upward, accounting for the narrowing cross-section. This curve traces the limits of the steel's integrity, from elastic limits to the ultimate strength. This comparison shows the distinct profile of a brittle material on the right. Unlike the ductile steel, the brittle material fractures suddenly, completely lacking a shaded plastic deformation region. Modern high-strength materials often lack a defined yield point. Engineers find safe working limits using the 0.2% offset method to determine proof stress. Materials can also fail through creep, a time-dependent process where permanent deformation occurs under a constant, unchanging static load over long periods. The stress-strain curve provides a unique performance profile for a material, dictating the precise conditions and mechanisms of catastrophic failure. We unify these material behaviors through 3 primary elastic constants: Young's modulus for linear elasticity, rigidity modulus for shear, and bulk modulus for volumetric change. These constants are locked together by fundamental equations. Because they are interdependent, changing one material property dictates the values of the others. This applies these relationships to a perfectly incompressible member, where volumetric strain equals 0. The algebra proves this physical boundary. To satisfy a 0 volume change, 1 minus 2 mu must resolve to 0, forcing Poisson's ratio to exactly 0.5. Elastic constants act as strict mathematical laws that bound the physical reality of all isotropic deformations. Look at a massive, tapering concrete bridge pier baking in the midday sun. To understand how it survives, we have to calculate for three specific extremes: its changing shape, its crushing self-weight, and thermal expansion trapped by rigid supports. Let's establish our physical baseline. Pressure is a scalar, and force is a vector. But stress and strain are tensors. They act on a specific plane in a specific direction. For a uniform bar, the baseline axial deformation is delta equals PL over AE. We are going to organize these conditions into a single framework, the deformation matrix. By the end of this lesson, we will build this row by row to help you solve these specific types of structural problems. This diagram breaks down the core variables. Notice the top right. Axial rigidity, or AE, is the product of the cross-sectional area and Young's modulus. It represents the combined contribution of the material and its geometry. A higher AE means lower axial deformation. Observe the bottom left and right. Rigidity is not the same as stiffness. Stiffness, K, factors in the length of the member to determine the load required for a unit of deformation. Flexibility is simply its inverse. Length changes how a member resists external forces. Correctly identifying these three variables is the starting point for predicting how a structural member will deform when subjected to axial forces. This graphic illustrates the principle of superposition for stepped bars in series. When a member has varying cross-sections, the total deformation is simply the algebraic sum of the individual section deformations calculated separately. For parallel composite bars, like a copper rod tightly encased inside a steel tube, the rule changes. The total load is shared between the two metals, but because they are physically locked together, their deflections must be strictly equal. Delta 1 equals delta 2. This image presents formulas for continuously tapering bars. For a circular taper on the left, there is a clear algebraic shortcut. Instead of the d² term used for uniform bars, you replace it with the product of the two varying diameters, d1 times d2. Rectangular tapering bars require a different approach. Because the area changes linearly along the integration bounds, the calculation requires a natural logarithm. You calculate the natural log of the ratio of the two varying widths, b1 over b2. These tapering shapes rely on the exact same physics as a simple uniform bar. We are just mathematically integrating that base formula over changing boundary conditions. This diagram shows deformations caused by internal gravity loads. You have to explicitly differentiate specific weight, lowercase w, from total weight, uppercase W. On the left, look at the prismatic bar. Its total deformation is exactly half of what it would be if all its weight acted as a single point load at the very free end. The formula becomes lowercase w times L² over 2e. In the center, a conical bar's total self-weight deformation is exactly 1/3 the deformation of a prismatic bar of the identical length. That gives us W times L² over 6e. On the right is the bar of uniform strength. Its cross-sectional area varies continuously along an exponential curve. This ensures the stress remains perfectly constant at every section, even as the accumulated weight increases toward the top. Self-weight acts as an internal accumulation, rather than a standard applied load. Managing it efficiently requires variable geometry. This graphic maps out thermal stresses along a restraint continuum. Look at Tier 1. Free expansion causes zero stress. If a material can freely change size when heated, no internal resisting forces develop. Thermal stress is born entirely from restraint. In Tier 2, rigid walls block 100. Because the physical desire to expand is denied, the bar experiences maximum compressive stress, equal to E times alpha times delta T. Tier 3 shows a yielding support. The wall gives way by a small distance, lambda. The only part of the thermal expansion that generates stress is the fraction actively blocked by the support. Try this. Pause the video and write the compatibility equation for a rigidly joined copper and steel composite that is being heated. Keep in mind, copper wants to expand more than steel. To reach equilibrium, the two materials must end at the exact same length. Because copper wants to expand further, the steel holds it back, forcing the copper into compression. Meanwhile, the copper drags the steel forward into tension. The internal forces balance out to zero. The relationship between heat and stress is straightforward. Thermal stress only exists when an object's physical desire to change shape is denied by its environment. Imagine a stepped bar with varying cross-sections, topped between two walls with a small yielding gap. experiencing a temperature spike. First, calculate unrestricted thermal free expansion. Then, subtract the gap and use the superposition formula to find the internal compressive force squashing the bar back. This is the synthesis deformation matrix, compiling formulas for axial loads, self-weight, and thermal loads across different conditions. Take a screenshot. Organizing boundary conditions and compatibility equations this way makes it much easier to handle axial deformation problems in structural exams. Preparing for this section isn't about memorizing every possible variation of a formula. It's about recognizing how a few core principles are adapted for the geometry of the problem.